In this video, I'll give some numerical examples about the radical chain polymerization. So first, some shorthand notations. I stand for radical initiator, R is radical, M denotes monomer, and X is the number of monomers in a radical chain. So let's first look at the mechanism. The radical initiator may decompose into two radicals. The rate constant is K sub I, and this is a first order reaction. It's a first order elementary reaction. Here's one example. I can be benzene, C double O, O, and then O, C double O, phenyl. The point is it's very easy to break this oxygen single bond and to form two radicals. So this step is called initiation. The second step is called activation. So the radical can react with a monomer. I'm going to use K sub 1 as the rate constant. And then we form Rm.1. This is a second order reaction. As you can see, we have two reactants. R dot, this is a radical, and a monomer. If you look at the coefficients in front of R dot and M, they're both 1. So this is a second order elementary reaction. So here I'm going to give you an example as well. This is a radical. It may attack a monomer, and then the result is the radical bonded to the monomer, and then we have a different radical. This is called a radical chain with a length of 1 because we have one monomer in this radical chain. Step 3, we call that propagation. We're going to make it more general, so we're going to say, well, R, M. Over here, I'm going to say, well, M minus 1 plus M. We're going to use K sub P for the rate constant of this propagation reaction. Over here, this is also a radical attacking another monomer, and then we have a longer radical chain. So over here we have minus 1 monomers. Here we have M monomers. This is also a second order reaction. Again, you can just determine this by looking at the coefficient in front of the radical and that in front of the monomer. All right, so for example, we can look at this example. All right, so let's say we have 30 monomers in this radical chain, and then you can react with another monomer. The result is, well, 31 monomers in the radical chain. And then number 4. In number 4, we can have two radical chains reacting with each other. So what I'm going to do is I'm going to just use two new variables here. I'm going to say, well, M, this is radical. N, this is another radical. Two radicals may recombine to form a single bond. And then we have the monomer. Actually, M plus M monomers in this product site. This is called termination because we're going to terminate the chain reaction initiated by the radicals. So I'm going to use K sub T here. And then we're going to analyze the kinetics of this mechanism. For convenience, I'm going to combine these two. Just say, well, these two are both propagation. So we're going to have the radical keep attacking monomers and grow the radical chain. So I'm going to assume this K1 and Kp are very close to each other. Well, it's reasonable because in both reactions, it's a radical attacking the monomer. Usually, this type of reactions are pretty fast because of the high reactivity of the radical. And K sub T is pretty fast because, again, this is a reaction between two radicals. K sub I can be small. This is because, after all, we need to break a oxygen-oxygen single bond. The bond strength is not as strong as many other bonds, but still you need external energy to break this bond. So K sub I is typically small. And also there's a difference here. If you look at step 1, this is a first order reaction. But step 2, step 3, I call them propagation. Those are second order reactions. And finally, if you look at the last termination reaction, it's also second order. So I'm going to put it here, second order. All right. Now I'm going to give you some numerical examples. First of all, we can apply the steady state approximation to the radicals. It's very important. When you have highly reactive species in the mechanism, usually you can apply the steady state approximation for such a highly reactive species. This is to assume the rate of change of the concentration of a highly reactive species is very close to 0 during the reaction. So in this case, the change of the concentration of radicals over time is roughly 0. All right, and this x can be 0, 1, 2, 3, etc. When x is 0, the radical is just R naught. When x is 1, you have Rm naught. When x is 2, it's Rmm naught. When x is 3, you have Rmm naught. So you have different challenges. Now we're going to look at this steady state approximation. So when we look at this, we need to realize that radicals are produced in step 1. So I'm going to mark it. All right. So in step 1, radicals are produced. In step 4, radicals are annihilated. However, in step 2 and 3, well, on the left-hand side, you have one radical. On the right-hand side, you have one radical. Same here. On the left-hand side, you have a radical. On the right-hand side, you have a radical. So in steps 2 and 3, the number of radicals remain unchanged before and after the reaction. So we just need to focus on step 1 and step 4. In step 1, how fast the radicals are produced, it's just simply Ki times I. But don't forget that when you decompose one I, you produce two radicals. All right? And not all radicals are able to initiate a reaction. So there's a success rate. Some radicals are just annihilated immediately after being produced. So this phi is usually less than 100%. The success rate is less than 100%. All right, and then it's equal to the consumption rate of the radicals. So what I will do is I'll do RT. All right, so this is RT times. This is a second order reaction, but over here you have M, you have N. In general, we're gonna just use X to denote M or N or 0 or 1 or 2 or 3. So this is just for convenience. It's just impractical to take account of all different kind of radical chain lengths. I'm treating all radical chains in a similar manner. So this is the reaction rate. But also don't forget, in one termination reaction, two radicals are annihilated at the same time or consumed at the same time. So you have a number 2 here. So this is the reaction originates from the steady state approximation. So over here, this is the production rate of the radicals. This is the consumption rate of the radicals. All right, when the production rate is equal to the consumption rate, we have the change to be 0. So again, this is the steady state approximation. Right, and then we can do some numerical example. Well, let's say Ki is 100 per second. Again, you need to pay attention to the unit. This is a first order reaction, so the rate constant is in reciprocal second. And let's say I is 10 to the power of negative 3 molar. We don't usually need a lot of I. maybe we can make it smaller, 10 to the power of negative 6. Okay. And let's say phi is 80%. That means when I decomposes into two radicals, not all such radicals can successfully initiate a radical chain reaction. Some of them are annihilated immediately. For example, they may be absorbed by the surface of the reaction container. KT. KT is usually pretty large because you can see this KT is the rate constant for the termination reaction. So I'm going to give you a fairly large reaction rate constant here. Let's say 10 to the power of 11. Now what's the unit? The unit is molar to the power of negative 1, second to the power of negative 1. Well, this is because it's a second order reaction. So the reaction rate is K times the reactant to the power of 2. You have two radicals. And if you do a unit analysis, you know the rate constant will have to be in molar to the power of negative 1, second to the power of negative 1. Again, this is just to balance the units of both sides of the equation for the rate constant. All right, so you have this. And then given this information, we will be able to compute the concentration of the radicals. So you just look at this equation and you can see all informations are given for us. So 2 times K sub I, 100, times the concentration of I, and then times 80%. Is equal to 2 times K sub T times the concentration of the radical chains. And again, X can be 0, 1, 2, 3, etc. So when X is 0, it's just R dot. When X is 1, it's just RM dot. It's explained up here. All right, and then 2 and 2, they cancel. You just move things around. Okay. You can compute the concentration of this guy. I think you just need to divide this unit with this unit, and this molar becomes, actually this is molar to the power of 2 now. And 10 to the power of 11. We change this to 10 to the power of minus 11 over here. And then over here we have this R M X dot to the power of 2 is equal to, let's see, this is 10 to the power of negative 17, 10 to the power of negative 15. Molar squared. All right. Since I'm only giving you an example, I'm not gonna focus too much on the actual value of the square root of 8. I'm gonna say, well, it's roughly 2.8. This is just my estimate, and then times 10 to the power of negative 8 molar. This is a very low concentration, and that makes sense because radicals are highly reactive. We are looking at this radical. You can call this radical chains or radicals. Typically, they have very low concentration, and over here you can see in my numerical example, you can see the concentration is very, very low, and in experiments, it's very hard to measure the concentration of the radicals. So over here, by using steady state approximation, we can estimate the concentration of the radicals. And now I'm going to give you another numerical example to compute the average kinetic chain length. The concept of this is just very simple. We're going to just look at the consumption rate of M. M stands for monomer. Divided by the production rate of radicals. All right, well, why is that? Well, just imagine within a, let's say, 1 nanosecond period or 1 microsecond period, just within a very short time of period, let's say 5 radicals are produced, and then 500 monomers are consumed. Where do these monomers go? These 500 monomers actually are bonded in sequence to the radical. And then, therefore, the average kinetic chain length is 500 monomers are being consumed divided by 5 radicals being produced. That's just 100. All right, so I'm going to just give you a simple example here. Within 1 nanosecond, it's just a random number. Let's say 500 m are consumed. How are they consumed? Well, they are just added to the radical chain. 5R are produced. And then the average kinetic chain length is just 500 over 5 equals 100. Okay? So this is the average kinetic chain length. Why it's called kinetic chain length? Because actually this number keeps changing throughout the reaction. Every single nanosecond, every single microsecond, the average kinetic chain length is different. But why do we need to look at this number? Well, this gives us a rough idea in the end, the average chain length of the polymer. All right, so now I'm going to give you a more complex example because we can have a more accurate description of the consumption rate of the monomer. So if we look at here, if we look at the step 2 and step 3, the monomer is consumed, right? So really, how fast the monomer is consumed? Well, just K1 times R0 times M plus Kp times M times this radical. But for convenience, I'm going to combine K1 and Kp with a reason. Well, if you look at the left-hand side, it's just a radical attacking M, a radical attacking M. Usually they are fast. So K1 and Kp are usually both a pretty large number, all right, but not as large as K sub t. So I'm going to make up the number. Let's say Kp is, let's say, 10 to the power of 9. This is the unit for the rate constant of second order reaction. Again, you need to be able to do unit analysis for second order reaction, elementary reactions. All right, so now I'm giving you this number, and then you can see the consumption rate of M. It's simple. It's just Kp times the concentration of the radical chain times M, because after all, the reaction is between this radical chain and M. This radical chain attacks M and then keep growing. So over here, this is consumption rate of M. And then we can just compute this given M. M is usually much larger than the concentration of M is usually much larger than the concentration of the initiator. So here we assume the concentration of initiator is 10 to the power of negative 6 molar. It's a very small number. And now let's assume the concentration of this M is maybe 0.1 molar, so it's much larger. And then we can do the calculation 10 to the power of 9. This is your Kp times the concentration of the radical over here. We computed this before using steady state approximation. And then we have the concentration of the monomer, which is 0.1. So after we do the calculation, you can see this and this cancel. So it's going to be about 2.8. The unit over here, this to cancel, 0.1 molar. So we get 2.8 molar per second. All right. So this is how fast the monomer is consumed. The rate is 2.8 molar per second. And then you do have the production rate of the radical. The production rate of the radical is right here. This is the production rate of the radical. All right. Again, when we made the steady state approximation, we assumed that the production rate of the radical is equal to the consumption rate of the radical, right? So over here on the left-hand side, you just do the calculation. You can see this calculation is going to give you 1.6 times 10 to the power of negative 4 molar per second. This is the production rate of radical. All right, you only produce radicals in the first step. In the second and third step, you're just changing the nature of the radicals. Only in the first step, overall, you have net increase of the concentration of the radicals over here. And the rate is 1.6 times 10 to the power of negative 4. So 2 times 80% is 1.6, and you have 100 here, times the concentration of I, you get 10 to the power of negative 4. So it's 1.6 times 10 to the power of negative 4. I'm going to write it here. The production rate of radicals is 1.6 times 10 to the power of negative 4, also molar per second. So again, if you're talking about reaction rate, it's always in molar per second. But if you're talking about rate constants, well, it depends on the order of the reaction. Now we have these two numbers. We have the consumption rate of the monomers. We have the production rate of the radicals. So we just do a simple division here. The units cancel. We got the average kinetic chain length. This is about 1.75 times 10 to the power of 4. Okay. All right. This is a very large kinetic chain length. So it tells you within that small time period, let's say 1 nanosecond or 1 microsecond, on average, the chain length is predicted to be roughly 1.75 times 10 to the power of 4 monomers per radical chain. So if you need an analogy, and if you play Lego, let's say within 1 second, I threw in 5 base plates in a room. In this room, there are many people keep adding Lego blocks on top of the base plate. And within 1 second, they consume, let's say, 500 Lego blocks. And then on average, I can tell within that time period, since we consumed 500 Lego blocks, in another way, we put 500 Lego blocks on 5 base plates. So within that time period, the average number of Lego blocks on each base plate is 100. So the average kinetic Lego block number is 100. So that's a simpler analogy used to explain the concept of average kinetic chain length.